You've been staring at that pot for 5 minutes. The water looks violent, yet it's still liquid. Here's what's actually happening inside. Most of us grew up thinking boiling was simple. Heat goes in, water turns to steam, done. But that's not what happens at all. What you're watching when a pot bubbles is something far more intricate, a battle between two states of matter playing out in microscopic arenas you've never seen. Let's start with what you can actually see. A bubble forms at the bottom of your pot. It rises, it pops at the surface. That bubble isn't pure steam. It's mostly water vapor, but here's the part most people miss. It only exists because the water near the heating element is hot enough to break free, while the water above it is still cool enough to pull it back down. Water boils at 100 degrees Celsius at sea level. But that's a threshold, not a magic line. Below it, water molecules are locked in constant motion, vibrating against each other. Heat them up and they vibrate faster. Faster still. At some point, a molecule at the surface has enough energy to escape into the air as vapor. That's evaporation. It happens at any temperature, even in your cold glass of water on the counter. But boiling is different. Boiling is what happens when bubbles form inside the liquid, not just at the surface. And that requires something counterintuitive. The water has to be hotter than 100 degrees in some places, even though the whole pot reads 100 on a thermometer. Here's where it gets strange. The metal of your pot conducts heat from the flame. That metal is now hotter than 100 degrees. Maybe 110, maybe 120. Water molecules touching that hot surface vibrate so violently they escape as vapor, forming a bubble. But that bubble is surrounded by cooler water at exactly 100 degrees, or maybe even 95. That cooler water collapses the bubble. It condenses the vapor back into liquid. This happens millions of times per second. Bubbles form, they collapse, form again, collapse. Most of them never make it to the surface. They're stillborn, destroyed by the cooler water surrounding them before they can rise an inch. Eventually, though, something changes. The whole pot warms up. Even the water far from the heat source begins to reach 100 degrees. Now the temperature gradient, the difference between hot and cool, shrinks. Bubbles form. And now there's less cold water around them to collapse them. They survive longer. Once the entire pot reaches a stable 100 degrees, something remarkable happens. Bubbles now form, rise, and pop at the surface almost unimpeded. The water is in true equilibrium. It's boiling. And here's the thing nobody talks about. Even now, most of what's escaping isn't pure steam. It's a mixture of liquid water droplets and vapor. You're not watching water turn to steam. You're watching a phase transition that's messier than the textbooks admit. Why doesn't the water instantly turn to steam? Because phase transitions need time. They need energy to be distributed. They need the entire system to reach a state where the conditions support the change everywhere at once. It's not enough for your burner to be hot. The water itself has to be ready. The next time you wait for water to boil, you're not just waiting for heat. You're waiting for a vast number of molecules to reach a critical point of agitation. You're watching chaos organize itself into a new state. That patience you feel, that's not wasted time. That's physics doing its work. Subscribe to uncover the hidden physics in the everyday. Each week, a new ordinary object reveals something extraordinary.